Part 2 on field effect transistors. Here we are touching on MOSFETs. MOSFETs and their characteristics. A MOSFET has a gate, a source, and a drain. The drain current in a MOSFET is controlled by VGS. There are two basic types of MOSFETs. The enhancement type, which are called the E MOSFET, and the depletion type, which are called the D MOSFETs. Unlike JFETs, the gate terminal in a MOSFET is insulated from the channel. Thus, MOSFETs are also referred to as insulated gate FETs or IG FETs. The input impedance of a MOSFET is many times higher compared to the JFETs because of the insulation. These two figures shows us the N-channel D MOSFET. A is the construction and B is the schematic symbol that you can use in a circuit. The block of P-type material forms the substrate into which the N-channel is embedded. Along the channel, a thin layer of silicon dioxide Si02 is deposited to isolate the gate from the channel. The substrate is usually connected to the source, thus results in a three-terminal device. D MOSFETs are normally on devices, meaning that ID flows even when VGS is equal to 0. Zero gate voltage. So here we have current in a JFET, in an N-channel D MOSFET. The current flow in an N-channel D MOSFET, which VGS equals to 0. This is how we will connect it, as shown in figure A. And then B shows you the drain curves, the relationship between ID and VDS. D MOSFETs can operate with either positive, 0, or negative gate voltages. When the P-type substrate is grounded, the N-channel and the P-type substrate are always reverse biased, resulting in 0 current in the substrate. The gate current is also 0 because of the extremely high resistance, several thousands of mega ohms, of the silicon dioxide. Operating characteristics. The D MOSFET have operating characteristics like JFET. See figure B on the previous slide. For each drain curve, the ID increases linearly until the VP is reached. When VGS is negative, the pinch-off occurs sooner, and when VGS is made positive, the pinch-off occurs later. Note that the maximum ID does not exist when VGS is equal to 0. IDSS is not maximum, but is still defined as the drain current with the gate shortened. Figure A gives us the drain current increases with a positive gate voltage. Figure B shows that the drain current decreases with the negative gate voltage. The positive gate voltage attracts the free electrons from the substrate, enhancing the conductivity. Thus, D MOSFETs are said to be operating in the enhancement mode. The negative gate voltage repels the free electrons from the channel. With negative voltage relative to the source, the D MOSFET is said to be operating in the depletion mode. Making the gate negative enough will reduce ID to 0. Transconductance curve. So this is how you will draw the transconductance curve. As VGS becomes more positive, the value of ID increases. As VGS becomes more negative, we have less and less ID value until it's ID 0. That's when we get the VGS off. To remember, IDSS is still the drain current that flows when the gate are shortened to the source. So it's still the maximum voltage, but it's not really the maximum, because if you supply a positive VGS, you'll get a higher value than this IDSS. VGS that reduces ID to 0 is still called the gate source cutoff voltage. designated VGS off. A DMOSFET is also a normally on device because there is an ID with 0 gate source voltage. ID can also be calculated using ID equals to IDSS open bracket 1 minus VGS divided by VGS off close bracket squared. And this formula can only be used when VDS is greater than the pinch off voltage VP. A DMOSFET has the following characteristics. IDSS equals to 10 milliamperes, VGS off equals to -4. Calculate the drain current ID and VGS. Okay, calculate the drain current ID for VGS equals to 2, VGS equals to -2, and VGS equals to 0. So for each of the following of the VGS listed, the calculations will be ID equals to IDSS open bracket 1 minus VGS over VGS off close bracket squared. So we use 10 milliamperes open bracket 1 minus positive 2 divided by -4, which is our VGS off. So we get 22.5 milliamperes. For B, this is when ID VGS is equal to -2, we get 2.5. When VGS is equals to 0, then ID would be equals to IDSS, which is 10 milliamperes. So if you notice on A, the value is higher than 10 because we used a positive VGS. So it's 22. From 10, it increased to 22.5. For B, we used VGS of -2. So meaning that the value of ID will drop to 2.5. For C, VGS is equals to 0, so ID will remain as our IDSS, which is equals to 10 milliamperes. P-channel DMOSFET. So P-channel DMOSFET, the construction and the schematic symbol on B. A P-channel DMOSFET they require a negative drain voltage. The arrow of the schematic symbol points outward. The transconductance curve shown below is opposite that of a N-channel DMOSFET. The P-channel DMOSFET operates in the enhancement mode when VGS is negative and in the depletion mode when VGS is positive. So here it will be it will be opposite of what the N-channel was showing us. Here when you supply a negative VGS, you are increasing the ID. When you apply a positive VGS, you decrease the value of ID. So the voltage that will cause ID to be 0 here will be positive VGS. So VGS off here is positive. Applications of DMOSFETs. DMOSFETs are frequently used in small signal amplifiers and frequency mixers. MOSFETs might be used instead of JFETs where very high input resistance is required. Enhancement type MOSFET, so the E-MOSFET. Figure A shows us the N channel of an E-MOSFET, the construction of it, and then B shows us the electric charge on surface of the silicon dioxide insulation layer. And then C shows us the schematic symbol that you will use in a circuit for a E-MOSFET. And then D shows us the drain curve showing us the relationship between ID and VDS on a E-MOSFET. The P-type substrate of an E-MOSFET makes contact with the silicon dioxide insulator. There is no channel for conduction between the drain and the source terminals when VGS is equal to 0, so ID is equal to 0. To produce ID, the positive gate voltage must be increased to attract electrons along the right edge of the silicon dioxide insulator as shown in figure B. The minimum gate source voltage that makes ID to flow is called the threshold voltage VGS-TH. When VGS is less than VGS threshold, then ID is equal to 0. The value of VGS threshold varies from one E-MOSFET to the other. MOSFETs are called normally off devices because ID is equals to 0 when VGS is equals to 0. The more positive the gate source voltage, the more the ID value. P-channel MOSFET. The biasing of a P-channel MOSFET, proper biasing voltages are shown in figure A, and then B shows us the transconductance curve. P-channel MOSFET. They require a negative voltage and drain voltage for biasing. P-channel MOSFET. For a P-channel MOSFET, ID is 0 until VGS is more than the negative threshold voltage VGS. The reason why MOSFETs are preferred in digital computer electronics over BJTs, they take up very little space on a chip compared to BJTs. They consume extremely little power compared to BJTs. MOSFET biasing techniques. We have the zero biasing D MOSFET. So this circuit in A shows us the common source amplifier using zero biasing. And then B shows us the transconductance curve showing how ID varies with a variation of VGS. The biasing technique is called zero bias because the DC potential difference across the gate source region is 0. When VGS is equal to 0, the quiescent drain current equals IDSS. When Vin becomes positive, ID increases. When Vin becomes negative, ID decreases. During the positive alteration of Vin, the D MOSFET operates in the enhancement mode. When Vin is negative, the drain current D MOSFET operates in the depletion mode. To calculate the DC voltage in the drain, VDS is equals to VDD minus IDSS times RD. It is common to select RD such that VDS is equals to VDD divided by 2. This means that RD is calculated as follows. RD will be equals to VDD divided by 2 times IDSS. Since it is a common source configuration, the voltage gain AV is calculated as AV equals to GM times RL. The biasing of an MOSFET, drain feedback biasing technique. The biasing of an MOSFET, A shows us the circuit using the drain feedback bias, and then B shows us the transconductance curve showing the values of VGS threshold, VGS on, and ID on. MOSFET cannot be biased using the zero biasing technique because VGS must exceed the VGS threshold to produce an ID. The figure above, or the figure on the previous slide, shows one way of biasing an MOSFET. This form of a bias is called drain feedback biasing. Example using the drain feedback biasing. Calculate the value of RD to provide an ID on of 10 milliamperes. So here, this transconductance curve shows us that the threshold voltage required for ID to flow is 1 volt. VGS on is equal to 10 volt. ID on is equal to 10 milliamperes. So RD will be equal to VDD minus VGS on divided by ID on, 500 ohm. Handling of MOSFETs. MOSFETs have one disadvantage, that they are extremely sensitive to electrostatic discharge. Extreme caution is therefore recommended when handling them. Precautions: never insert or remove a MOSFET from a circuit with the power on. Never apply input signals when the DC power supply is off. Wear a grounding strap on your wrist when handling a MOSFET device. When storing MOSFETs, keep the device leads in contact with conductive foam, or connect a shorting ring around the leads. This is where we end it. We'll do more examples in class.